magnesium carbide, Mg2C3. This time you should know the structure of Mg2C3. C, double bond C, double bond C, magnesium, magnesium. Break the bond, HOH. You end up getting CH2, double bond C, double bond CH2. You collect the pieces, CH2, double bond C, double bond CH2, and of course magnesium hydroxide, MgOH twice. So if you simply hydrolyze Mg2C3, break the bond, 4H4OH, 4OH 4H. Of course you get C3H4. You don't know what that C3H4 is. That C3H4 can be propyne or propadiene. This is propadiene, propadiene, also called ellene. But ellene being less stable, in course of time that becomes propyne, C triple bond C. But that is not our concern here. What happens to an organic compound is should not be our concern now. So magnesium carbide gives ellene. So now look at what do you get on the hydrolysis of carbides. Carbides on hydrolysis, I told you H3O plus is a symbol for hydrolysis. Carbides on hydrolysis give, what do they give? What is it you have seen? You have seen acetylene in calcium carbide, methane in beryllium and aluminum carbides, and this one propadiene, which is called ellene. Mind you, propadiene is also called ellene. The 2012 question, the hybridization of carbon in ellene is, you have two carbons, one with sp2, the other one with sp. So H3O plus. Carbides and hydrolysis give hydrocarbons. Hydrocarbons. Carbides which give methane on hydrolysis are called methanides. Methanide, carbides that give methane on hydrolysis. Acetylide, you should know the definition from the meaning. Carbides that give acetylene on hydrolysis. Allylides, carbides that give ellene on hydrolysis. Once again, carbides, those give allenes, those cumulated dienes, carbides, those give allenes on hydrolysis, are called acetylides, carbides. So hydrolysis of carbides, what do you get? Next set. Let us hydrolyze some of the nitrates. Magnesium nitrate, Mg3N2. What do you get on the hydrolysis of magnesium nitrate? First step, you remember, break the bond, HOH. Where will H go? Where will OH minus go? OH minus goes to magnesium plus, magnesium that is plus. 6OH. Why am I opting for 6OH minus? Every time I am not writing this minus and plus, because it is not necessary. It goes without saying H is H plus and OH is OH minus. And now, magnesium nitride. Why have I taken 6? Magnesium, the valency is 2, belongs to the second group, electrovalency 2. So 3 into 2, 6. So strictly speaking, 3 MgOH twice plus NH3, 2 ammonias. Nitride, IDE means, mind you, 1 capital negative. 1 capital. Nitride, nitrogen and some minus, be it N minus 1, minus 2, minus 3. In the case of nitrogen, you know it is N3 minus. Carbide, carbon with 4 minus. Even silicaide for that matter, silicon with 4 minus. So ID, chloride, bromide. Okay, all negatives are not called. You look here, Cl minus, Br minus, oxide, even ozonide for that matter. Ozone, ozonide, sulfide. But you can't talk about sulfate, sulfate, where you have 2 capital letters. No, this is not an ide. That is not an ide. ID means only 1 capital letter. I wanted to say elemental anion. How difficult for me to say that, you see. You won't even get the complete picture. Elemental anion. Then I have to say what an element is, where you have only 1 capital letter. Element, 1 capital letter. So instead of saying that, 1 capital means just 1 atom. 1 type of atom, only 1 types of atoms. All similar atoms, Cl minus, Br minus, O2 minus, O3 minus. Magnesium nitride. Aluminium nitride. Break the bond. 3OH, 3H. Ammonia. I am not interested in the hydroxide. AlOH, metal hydroxides, metals when they are in water, you get their hydroxides. There is no big thing. Metal hydroxide. NH3. So, what we have indirectly did is preparation of ammonia. Suppose if I ask you, how is ammonia prepared? Ammonia is prepared on the hydrolysis of nitrides. You already seen magnesium nitride, aluminum nitride being hydrolyzed. And now, phosphide, zinc phosphide, which is poisonous for rats, rat poison. Break the bond. 6OH, 6H. You get PH3. Phosphide, you know phosphide is P3 minus. Since it is P3 minus, you get PH3, 3 plus plus. So phosphine. Carbides and hydrolysis give, carbides you have seen, carbides and hydrolysis give hydrocarbon, hydrogen and carbon. Hydrogen plus and carbon minus to be very precise. Nitride gives ammonia where nitrogen is minus, H is plus. Phosphine where phosphorus is minus, H is plus, phosphine. And now the relevant halides, hydrolysis of halides. BCl3. BCl3. What will you do? Break the bond. 3H, 3OH. Are BOH thrice. H3BO3. Boric acid, and of course HCl. What you should remember is I have broken 3 bonds. If you want me to clarify, I would say BCl3. You have to break every bond. HOH, HOH. This is rather clumsy, therefore don't do that. Break 3 bonds, 3H. So instead of writing the structure and breaking 3 bonds, break the bond 3H, 3OH, BOH thrice. But there are some people who won't sleep until they write BOH 4 times minus. Some people give this as the product. Of course, this is a product, I agree. But you need not be very particular. Once boric acid is in water, this is how it reacts with water, boric acid. So here I am talking about reaction of BCl3 in water. You get H3BO3 and H3BO3 in water gives this. But BCl3, okay, first step, second step. You need not be worried about this. What happened? BOH, 1 OH minus is being, 181 is involved. Now, BCl3. Break the bond. 3 OH, 3H. POH thrice. H3PO3, phosphorus acid. I have not written phosphorus acid. You know it's an acid. You know it is phosphorus. Therefore, phosphorus acid, PCl3. PCl3 on hydrolysis gives POH thrice. PCl5. break the bond, 5OH, 5H, POH 5 times, of course 5HCl. I am writing only the main product, POH 5 times, POH. What do you know about phosphorus? It can't handle more than 3 OH groups. It can't handle more than 3 OH groups. Automatic loss of water, because phosphorus, if you remember, maximum number of OH is only 3. Higher than 3 OH groups, more than 3 OH, automatic loss of water. So what is it you end up getting? POOH thrice, POOH thrice, which is nothing but H3PO4 phosphoric acid, ick, phosphoric acid. So no harm in writing H5PO5. H5PO5 is also okay. You can say it is hydrated phosphoric acid, H3PO4 dot H2O, dot H2O. But since we are familiar with this H3PO4, we write this. Now PCl5 on hydrolysis gives H3PO4. The same PCl5 on partial hydrolysis, it should be clearly mentioned, partial hydrolysis, partial hydrolysis. Only 2 chlorines will undergo hydrolysis. So you end up getting POH, OH, only 2 bonds are broken. The remaining 3 chlorines are not, broken. Only 2 chlorines you can see, 2 OH in presence. But even these 2 OH also, you will end up getting POCl3. You may get a doubt, why phosphorus, even though it can handle 3 OH groups, losing water molecule? Because POCl3 is tetrahedral, geometry matters. This POH twice and Cl3 is trigonal, bipyramidal. Tetrahedral is a better geometry. So PCl5 on partial hydrolysis gives POCl3. So if the question is PCl5 on hydrolysis gives, it is phosphoric acid only. If they clearly mention partial hydrolysis, unless the partial is mentioned, the answer is H3PO4. Now SbCl5 and BiCl5, SbCl, BiCl5, I would say SbCl3, SbCl3 and BiCl3, because bismuth doesn't prefer to form pentahalides due to inert pair effect. So SbCl3, BiCl3, they undergo partial hydrolysis only. To give SbOCl and BiOCl. They undergo partial hydrolysis only. Whereas in the case of PCl5, you have both the hydrolysis. Here they undergo only partial hydrolysis. Only 2 chlorines are broken and 2 OH groups, the water molecule is removed. Perhaps you may have to remember this separately. So instead of mugging up 100 reactions, 95 reactions follow the general procedure. The peripheral reactions, 1 or 2 reactions, you learn them separately. That is how one has to study. Wherever there is a generalization, wherever there is a common factor, you study them that way. And if some reactions are out of the ordinary, in what you call exceptions, you just learn them separately. Next, NCl3. NCl3. Break the bond. H plus on one side, OH minus on the other. But where does H plus go? Whoever is more electronegative. Our list says F greater than O greater than N greater than Cl, greater than H greater than boron, What is this list for? Electronegativity. You will get the other non-metals like bromine, iodine, sulfur, phosphorus, carbon, silicon. You have only very few elements here: bromine, iodine, sulfur, phosphorus, carbon, silicon. Only 5-6 elements are there here. After boron, you have the half metals and of course metals after boron. But look at hydrogen and boron. Hydrogen is more electronegative than boron. Now, NCl3. Nitrogen is more electronegative. So, H plus goes here. 3H plus, 3OH minus. The answer you have to write is ammonia once again. And 3HOCl, hypochlorous acid. Hypochlorous acid. Of course, in a different chapter, we learn why this is called hypochlorous acid, or what do you mean by hypo. We learn in a topic called oxyacids separately. And now, so how is ammonia prepared? Hydrolysis of nitrates. We have seen magnesium nitride and aluminum nitride on hydrolysis giving ammonia, and NCl3 also giving ammonia. You already seen that. Now, so Pauling, according to the Pauling electronegativity scale, Pauling has given nitrogen and chlorine same electronegative values, 3 Pauling. According to Pauling scale, the electronegativities of nitrogen and chlorine are like this. And Allred Rochow went a step ahead, saying nitrogen is 2.9 and chlorine is 3.1. According to Allred Rochow scale, some scale, electronegativity scales, which are like rating scales. You can say it's their perception. They thought it is 2.9, Allred Rochow scale. So, how can we know which is more electronegative? This reaction settles all discussions, mind you. When NCl3 is in water, H plus is preferably attacking nitrogen because nitrogen is more electronegative. Okay, H plus knows better. H plus knows where it has to go. It's not for me to decide that nitrogen is more electronegative than chlorine. It is hydrogen that has decided that nitrogen is more electronegative. So, this reaction settles all discussions about the greater electronegativity of nitrogen. So, we have hydrolyzed many SiCl4, boron from the third group, silicon from the fourth group, phosphorus, fifth group halide. So, I am not discussing halides of group 5. You have seen I am discussing halides of group 3, 4, 5, 6, what not. Even sulfur, SCl4 or SCl6, you can hydrolyze SCl4. Break the bond, 4H, 4OH. What should sulfur do? 4 OH groups. You know it can't handle more than 2 sulfur, only 2 OH groups. Because OH minus groups are highly electron withdrawing, the central atom positive charge is developed, and because of the positive charges all around due to the repulsions, water automatic loss of water. Now, SiCl4. So, what is it? H2SO3, sulfurous acid. SCl6, sulfuric acid. So, halides of 6th group. So, you have halides starting from the third group: boron, silicon, nitrogen, phosphorus, sulfur. So, all in every group, if you discuss group 16, group 17, group 15 separately, you have to study this reaction. SiCl4, 4H, 4OH. This is SiOH 4 times. You know silicon can handle 4 OH groups because it is electropositive. If you observe that list, silicon, phosphorus, sulfur, chlorine, 1, 2, 3, 4. It is the number of OH groups. So, as the electropositivity is increasing, you know silicon is more electropositive, it can tolerate more and more OH groups. Silicon can handle 4, phosphorus 3, sulfur 2. So, when you go from left to right, 4, 3, 2, 1. The tolerance towards OH groups, the electron sucking OH groups, the tolerance is decreasing. Chlorine doesn't tolerate more than 1 OH. SiCl4 on hydrolysis you got H4SiO4, which is called orthosilicic acid. I would simply call it IC. You know it's an acid, you know it's an acid of silicon, and ortho is an optional term. Ortho, whether you use it or not, doesn't make any difference. Ortho is like Mr. Silicic acid, orthosilicic acid, a title. Ortho is almost like a title, okay, silicic acid. So I simply wrote IC because you know that this is an acid, you know that it's an acid of silicon, and this term ortho is optional. So which word is important? Silicon, acid, ortho, they are not important, only IC. Therefore, H4, what is the name of H4SiO4? I simply say IC. Chloric acid, instead of saying chloric acid, I say IC. Instead of saying orthophosphoric acid, I simply say IC. Why? H3PO4. The correct technical name is orthophosphoric acid. Phosphoric acid. Ortho is optional. You know that this is an acid and you know this is an acid of phosphorus. So the only important word is IC. IC, us, hypo us. So you should know what that particular prefix mean. Now, orthosilicic acid. So towards the end of halides, we started discussing acids, oxyacids. So the natural heading will be oxyacids. I am not forcing any heading here. I am not creating a heading artificially. The halides, the important reaction is hydrolysis, and hydrolysis of halides, you get oxyacids. So you should, next heading should be oxyacids, and of course our next discussion will be on oxyacids. But let us look at a few more hydrolysis things here. Halides. B2H6, very interesting, diborane. How does diborane react with water? Though we don't call it hydrolysis, you can definitely call it reaction with water. Break the bond as usual. And who is plus, who is minus? You remember that? FONCl. H greater than B, hydrogen is more electronegative than boron, minus plus. So you have to give H plus here, 6H plus and 6OH minus. What is it you end up getting? BOH thrice once again. 2 borons and 6 OH. 2:6, 1:3. BOH thrice. And H minus and H plus, 6 molecules of hydrogen are liberated. Hydrogen gas. These 6 are minus, H minus. These 6 are plus, H plus. H minus, H plus, you get H2. And BOH thrice as usual is called H3BO3, orthoboric acid. Orthoboric acid. Acid, boron, ortho, IC once again, IC acid. IC. The emphasis is on IC, the stress is on IC. Now, so diborane and hydrolysis gives boric acid. So we have already seen 2 reactions in which boric acid is the product. What was the first one? Halides of boron, BCl3. BCl3 on hydrolysis give boron trichloride, gives boric acid. Diborane gives boric acid. Now let us extend this logic to some compounds containing carbon. Chloroform, CHCl3. What does it contain? You know the structure. It contains 1 carbon hydrogen bond, 1 hydrogen, 3 chlorines. And I told you, you might have forgotten, carbon hydrogen bond doesn't undergo hydrolysis. Look here, CH, Cl, 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 break the bond, H, OH, H, OH, H, OH. Be careful. I have broken 3 bonds. The 4th carbon hydrogen bond, the 4th bond carbon hydrogen I am not breaking, because carbon hydrogen, there isn't much of a polarity. There isn't much electronegative difference. Therefore, If it's not polar, you cannot break. At least water cannot break. H plus OH minus water being polar, it reacts with polar things only. Like this. Break the bond. 3H, 3OH. So chloroform on hydrolysis, what is it you ended up getting? Hydrogen, carbon, 3 OH groups. And what do you know about carbon? It cannot handle more than 2 OH groups. 1, 1, 1. Carbon handles only 1 OH. So automatic loss of water. HCOOH, you get formic acid. Formic acid. Chloroform on hydrolysis. Chloroform on hydrolysis gives formic acid. That's the reason it is called chloroform. A substance that eventually gives formic acid when dissolved in water. Chloroform. Formic acid. So some compounds under some conditions undergo hydrolysis. ROR, ether, break the bond. RCOOR, the esters, break the bond. HOH, esters, anhydrides, amides, ethers, all organic compounds containing a carbon-oxygen single bond. I repeat, a carbon-oxygen single bond will undergo hydrolysis. Right. And the cliche, last but not the least, cyanides, RCN. Cyanides on hydrolysis give. Cyanide. You know there are 3 bonds. Break the bond. 3H, 3OH. RCOOH. Bas. RCOOH. Cyanides on hydrolysis give carboxylic acids. Cyanides on hydrolysis give carboxylic acids. So wherever there is polarity, where should we break the bond? Wherever there is polarity. Where should we break the bond? Wherever there is polarity. And if the polarity is too much, I warn you, it's not very difficult to hydrolyze. It becomes very difficult. Let me teach you hydrolysis of xenon fluoride, which I told you, which I asked you to study from NCERT. This is not my responsibility. You have to study those 2 or 3 reactions separately, specially. You have to memorize them. Every year, almost there is a question on even the 2014 advanced, the hydrolysis of XeF4, I believe. XeF4 is one question. Break the bond. Why? Why do you need to study that separately? I am telling you. 2H2OH. Of course, until here we have discussed it. XeOH twice. 2HF, hydrofluoric acid. Hydrofluoric acid, the one in which glass dissolves. Hydrofluoric acid is used in the etching of glass. The etching of glass. I think the 2011 matching contains one of the products is used in etching glass. Etching glass. HF. So what do you know? In continuation, you know, xenon cannot handle even a single OH. Like silicon can handle 4 OH, silicon 4, phosphorus 3, sulfur 2, chlorine, bromine, iodine, carbon, etc. only 1. Beryllium and xenon, I told you, none. They won't even handle a single OH group. Therefore, remove. You got XeO. Until here we can use the procedure, but in extension to this becomes Xe plus half O2. So even that XeO also easily decomposes to give xenon plus half oxygen. Our procedure does not contain this. In our procedure, break the bond, HOH was there. Xenon cannot handle a single OH was there. I have removed water. Until here, it's according to the procedure. But the last step, I never told you what to do with XeO. Therefore, you study the hydrolysis of xenon fluoride separately from NCERT. Calcium cyanamide, CaNCN. This can even be called CaCN2. Calcium cyanamide. Calcium cyanamide. Calcium carbonate, when heated with graphite, you get calcium carbide. Calcium carbonate, limestone. When you heat that with graphite, you get calcium carbide. Calcium carbide, when heated with N2 nitrogen, you get CaNCN plus N, which mixture is called nitrolime, of course. And this calcium cyanamide on hydrolysis, calcium cyanamide, you hydrolyze calcium cyanamide. This I have taken only as an example of where to hydrolyze. Break the bond wherever there is polarity. Calcium 2OH, okay. Nitrogen 3 hydrogens, okay. 3 hydrogens. As usual, carbon 4OH, because you are breaking 4 bonds. So forget calcium hydroxide being one of the products. NH3, NH3, 2NH3 being one of the products, 2NH3. Ammonia is already manufactured. This is manufacture of ammonia by cyanamide process, and you have got COH 4 times. What is this COH 4 times? You know carbon cannot handle more than 1 OH, automatic loss of water. So this is CO2 plus H2O, carbonic acid. Carbonic acid is, of course, it's more like a mixture than a compound. Carbonic acid, a mixture of carbon dioxide and water. And you already have this calcium hydroxide plus 2NH3, and you get your CaCO3 back, calcium carbonate. So start with calcium carbonate, graphite, or the ingredients or the raw materials, calcium carbonate and graphite and nitrogen. You get cyanamide, you hydrolysis. So how is ammonia prepared? Hydrolysis of nitrites, hydrolysis of NCl3, and finally hydrolysis of cyanamide. This is called manufacture of ammonia by cyanamide process. So it looks very clumsy, but you just break the bond. Calcium 2OH, NH3, another nitrogen, another NH3. See, carbon, I have given 4 OH groups. But that doesn't retain a single OH. Carbon doesn't retain even a single OH. So we have discussed oxides and halides. If you remember the 15 columns we have written about group 5, but never do I discuss group 5 in isolation. We are discussing oxides of all p block elements, if not all elements. In fact, we discussed oxides of all elements. Halides, okay, halides we confine to, p block we were not discussing metal halides because that's a little out of the way here. And now oxy acids followed by hydrides. We just have 2 more areas in the biggest part of inorganic chemistry. Inorganic chemistry is strictly periodic table plus chemical bond plus p block. This is one exclusive part of this one. And chemical bonding, we don't discuss much on ionic bond because there's not much to discuss on ionic bond. It's like ionic bond is electrostatic attraction. How many types of electrostatic attractions will be there? Electrostatic attraction is only one type. But while sharing electrons, the covalent bond, so we mostly discuss, this is all about non-metals. If you look at the second part, p block, we are discussing mainly, in p block we are mainly discussing non-metals, and what is remaining, you will be surprised. These three topics, periodic table, chemical bond, p block, this is one part of inorganic chemistry. And of course, periodic table, periodic properties are essential for metals also. Look at the topics that are remaining. The topics that are remaining are S and D block, SD blocks, metals, metallurgy, all about metals, coordination compounds. Who forms coordination compounds? Coordination compounds are formed by none other than the transition metals, D block, S, D and F block elements. Metallurgy. coordination compounds, and qualitative analysis. Qualitative analysis mostly it contains cations which are metals, anions. So it's about a qualitative analysis is a bridge between, you can say, non-metals and metals, because the cation is a metal, the anions mostly are formed by sulfate, chloride, etc. Anions are formed by non-metals generally. So qualitative analysis, you analyze, you find out which cation and which anion. Cations are metals and anions. So qualitative analysis is, you can say, is a bridge qualitative analysis. And hydrogen which is altogether different hydrogen. This is it. So you can say we have metallurgy, S block, D block, all the properties of metals are almost the same. I don't say they are exactly similar. All metals behave almost in a similar manner, but non-metals have varying behavior, like nitrogen forms bonds leaving a lone pair, carbon forms bonds without leaving any lone pair. So this broadly inorganic chemistry, now you must have realized P block contains non-metals, means half of inorganic non-metals. And so the moment we started P block hardly 3-4 hours ago, but we are seeing, you can say 50% of P block, I mean non-metals, I mean inorganic chemistry. Oxy acids. My definition of oxy acid begins with H and ends with O. A formula beginning with H and ending with O. Oxy acid, acid that contains oxygen and hydrogen. Instead of giving a qualitative definition, I give a functional definition. Even a small child should be able to say. We should begin with H, end with O. H3PO4. Ah, yes, sir, this is an oxy acid. HClO3, HO. So, HO, oxy acid. So, when I ask you, what is this? H4SiO4. Sir, this is an oxy acid, you can easily say. Okay. Even H2CrO4 is an oxy acid. Of course, metal, chromic acid, oxy acid. Now, most important thing in oxy acids is their names. If you know the name, you can do virtually anything. The name is what is important. Now, ortho -ic acid. This term ortho is optional. This term ortho is optional. Ortho -ic acid. HNO3, H3PO4, H2SO4, HClO3. You take this as the reference point. Listen to me. These four are not my responsibility. You have to memorize. Nitric acid, phosphoric acid, sulfuric acid, chloric acid. And the three are very common. If you have any doubt, it may be about HClO3, chloric acid. There is some doubt about chloric acid, whether it is HClO3 or HClO2 or HClO4. So, make your minds clear. You learn these four oxy acids. I now tell you to give the formula of roughly 60-70 oxy acids. We have 60-70 oxy acids in the syllabus. Oxy acids of nitrogen, phosphorus, even arsenic, antimony, sulfur, selenium, tellurium, chlorine, bromine, iodine, all of them form oxy acids. Silicon, boron, they form oxy acids. And there are some 12-13 non-metals. On an average, they form 6 oxyacids, 6 types of oxyacids. Roughly we have 60 oxyacids. And how to remember the names of all the 60, you would better. And this term or though, I repeat, is optional. So you can say this is orthonitric acid or simply nitric acid, orthophosphoric acid or simply phosphoric acid. Ortho is optional. The emphasis is on ic, my dear friends. Ic. Nitric, phosphoric, sulfuric, chloric. Chloric. I won't even say chloric acid. Orthochloric acid. Orthochloric acid. Ortho is not necessary. Chlor is not necessary. Acid is not necessary. What is necessary is only ic. And now, us acid. Us means one oxygen less. Us means less. Us means less. Like the old notation cupric, cuprous, cupric, copper 2, cuprous, copper 1, copper 2 and copper 1, copper plus 2, copper plus 1, cupric, cuprous, ferric, ferric is 3, ferrous is 2, ferric, ferrous, mercuric, mercurous, stannous, stannic, stannic, ic, 4, us, stannous plus 2. So it's no big deal. Us means less. What is less? Us means one oxygen less than ic acid. HNO3, HNO2, H3PO3, H2SO3, HClO2. Look at it once again. Nitric, nitrous, phosphoric, phosphorus, sulfuric, sulfurous, chloric, chlorus. Ic, us. Nitric, one oxygen less, nitrous. So what's the difference between a nitric and nitrous? Just one oxygen, that's all. Phosphoric, phosphorus, sulfuric, sulfurous, chloric, chlorus, chlorus acid. Orthochlorus, once again, orthonitrous, orthophosphorus, no harm, because ortho is like Mr. phosphoric acid. Hypo dash dash us acid. Hypo dash dash us acid. Hypo means one more oxygen less. One more oxygen less. HNO. HNO twice. H3PO2. Why is this twice? Because hyponitrous acid, HNO, exists as a dimer only. So slowly we are heading towards dimers. So now the next list will be all molecules that will exist as dimers, trimers and polymers. You round off these two, H3PO3, H3PO2, and you put a dash here, HClO. I'll tell you why. Why are these two rounded off? You know, all other acids, the number of OH groups is equal to number of hydrogens present. 3, 1, 1, 2, 2. How many OH groups are there in hyponitrous acid? H2, 2, 2, 2, 1, 1. Number of OH groups is equal to number of hydrogens present was a generalization. These two are exceptions to that generalization, H3PO3, H3PO2. Why have I put it twice here? This one, HNO, exists as a dimer. How can you remember? Yes, of course, we have a separate, we will make a separate topic on called nit, and you know the reason also in that topic why nitrous acid exists as a dimer. And H2SO3, H2SO2 doesn't exist. Sir, how do I know that hyposulfurous acid doesn't exist? You need not know. If there is a question on what is the formula of hyposulfurous acid, don't hesitate to say H2SO2, because somebody is trying to fool you, you fool him as well. What is the formula of something that doesn't exist? You give a formula that doesn't exist. What is the formula of hyposulfurous acid? You say politely H2SO2. Does it exist? You have to say I do not know. I don't worry about existences. You asked me the question, I gave you the answer. That's all. Now, chloric, chlorus, hypochlorous acid. Hypochlorous acid. The ic, the us and the hypo. In fact, hypo means less, the opposite of hyper. Hyper, hypo, hypo. Hypo means it's per, more, less. Hypertension, high blood pressure. Hypertension. Hypertonic solutions whose osmotic pressure is more. Hypotonic, less osmotic pressure. Hypotonic, hypo. You even have that hyperconjugation. It's a little too much. Hyperconjugation is a little too much. Okay. Hyper. Now, so one line above, what will you write here? Since you are writing 1, 2, 3, mathematically you have to write 4. 2, 3, 4, 5. 3, 4, 5. 1, 2, 3, 4. Therefore, 1 oxygen more, HNO4, H3PO5, H2SO5, HClO4, HClO4. 1 oxygen more, they are called per or peroxy -ic acid. Per, simply per or peroxy -ic acid, but let me warn you, this one is per only. What does it mean? That's not peroxy. So this is per nitric as well as peroxy nitric. You even have a peroxy bond, per nitric, per phosphoric, per sulfuric. Per nitric, per phosphoric, per sulfuric, per chloric, per only. Per nitric, peroxy nitric, per phosphoric, peroxy phosphoric. 1 oxygen. Why are they all called peroxy? Because they contain a peroxy bond, oxygen single bond. How do you know? We even discussed. You just give -2 for oxygen, -10, and phosphorus is getting +7, which is higher than its group number. When you give -2 for oxygen, the other atom gets higher than group number, then it's a peroxy. H2SO5, same is the case with H2SO5, -10 +2 +8. But that the one doesn't contain a peroxy bond. HClO4 is not doesn't contain a peroxy bond, strictly speaking. Though I said that ortho doesn't have carry much meaning behind it. Now let us give some respect to this ortho. Let us give some significance to add some significance to that also. Ortho means maximum number of OH. Maximum number of OH groups that a particular atom can attach to. For example, orthosilicic acid. Orthosilicic acid. Orthosilicic. What would you say about it? Orthosilicic acid. Silicon with maximum number of OH. How many? SiOH 4 times. Which is nothing but H4SiO4, orthosilicic acid. Orthoboric acid. Boron with the maximum number of OH groups. Orthoboric acid. Boron with 3 OH. H3BO3. Ortho. In general, orthoic acid means ortho and ic means more maximum number of OH. Now, the next one we have discussed ic, us, hypous, peric, or for that matter peroxyic, ortho. We are discussing prefixes and suffixes. You will be surprised. By learning what that prefix suffix means, we can learn the name. Once you know the name, what is it you can do? You can do miracles. You can draw the structure. You can find the oxidation state. You can find the number of OH groups, which is called basicity. It's nothing but basicity. And how? So, ortho. Next prefix is Pyro. Pyro means acid plus acid minus H2O. Acid plus acid minus H2O. Pyrophosphoric acid. Pyrophosphoric acid. H3PO4. What do you mean by pyro? Acid plus acid. Which acid? You have to take two acids. I mean the same. Pyro means acid plus acid minus H2O. Pyrophosphoric means you take two phosphoric acid, H3PO4 plus H3PO4 minus H2O. H4P2O7. H4P2O7. H3PO4 plus H3PO4 minus H2O. H4P2O7. Pyrophosphoric acid. By the same way, pyrosulfuric acid. What is it you should do? You should take two sulfuric acid, H2SO4 plus H2SO4 minus H2O. Pyro means which acid should I take? The acid in question, he is asking about pyrophosphoric, you take phosphoric. Pyrosulfuric, you take sulfuric. Pyrosilicic, you take silicic. So, pyro is an adjective. Pyro is an adjective to sulfuric acid. Pyro means sulfuric acid plus sulfuric acid. It is like taking two molecules and removing water, that is called intermolecular dehydration, removing water from two acid molecules. H2S2O7, pyrosulfuric acid. Pyrosilicic acid. Silicic acid plus silicic acid minus H2O. How is that? Silicic acid plus silicic acid minus H2O. What is silicic acid? Ic. What do you mean by ic? Ic means ortho. What do you mean by ortho? Ortho means maximum number of OH. So, silicic acid, first of all, let us look at orthosilicic acid. Orthosilicic acid, which is nothing but SiOH 4 times, which is nothing but H4SiO4. This is the background. We know orthosilicic acid is H4SiO4, and this H4SiO4 plus H4SiO4 minus H2O, you end up getting H6Si2O7, pyrosilicic acid. What is the benefit? What is the benefit? I ask you, what is the basicity of pyrosilicic acid? How many OH groups are there in pyrosilicic acid? You can't answer that question unless you know what is pyrosilicic acid. If you know pyrosilicic acid is H6Si2O7, you can draw its structure, you can find the oxidation state, you can find the hybridization, and you can dare say number of OH groups is equal to 6 because you have H6. Okay, number of OH groups is equal to number of hydrogens present except those two acids H3PO3 and H3PO2. I already told you. Basicity 6. What is the basicity of pyrophosphoric acid? A moment ago we discussed pyrophosphoric acid. H4P2O7. The 4 is